usual, so I am going to open it up to the general audience. In fact, I'm going to be more than open it up. I'm going to ask Tim Eastman to comment on the epistemological questions, since he's studied these a lot. But then anybody in the audience to ask questions.
Oh, well, both issues in philosophy of science and history and my own area of space plasma physics. Concerning the latter, in my active work in space plasma physics, I came to really understand that it was essential to understand that in space plasmas, we're not working with just any one gravity or electromagnetism plasmas. Inevitably, we're working with both of them. And indeed, in my 60+ papers over my career, it just turned out, working with my space plasma phenomena, that I never had to refer to gravity because it was so negligible. And so in a way, in cosmology, you have almost the reverse. People that assume that gravity is presumed dominant, and therefore we can neglect or even assume 100% shielded electromagnetism and plasma effects. Well, these are both approximations under the conditions, and so it's all a matter of, well, what are the applicable approximations for the regime we're working in? Now, in terms of the predictive capabilities, notion of prediction, well, of course, strictly speaking, a prediction is something about a future experiment or observation, and something that's already happened is a postdiction, strictly speaking. And postdictions are very useful and very important because they help check the consistency and coherence and reliability of our predictive capabilities and algorithms. But to really get a robust test of a model to really neutralize the effect of, say, unlimited adjustments or fitting of data to or of a theory to data, then we really need good prediction, as Eric emphasizes. So I wouldn't say it's too much of a strong, there's a continuum here in terms of methodology. Certainly a lot of good science has been done within the Big Bang Research Program, and it made various predictions. It's enabled the lambda CDM model, which is a specific falsifiable model. It's a good scientific model because it's specifically infalsifiable. Now, I think productively, we've found that it's very specifically falsified. But we still have an ongoing Big Bang Research Program, I think, in terms of the philosophy of science work of Imre Lakatos, to make that distinction of a research program and a specific falsifiable model. Well, we'll see out of this falsification of the lambda CDM if a new falsifiable model can be adequately formulated within that Big Bang Research Program or not. I have my doubts given what I've heard in the last few years, especially in the last couple months, but we shall see. So I think we have emerging from this discussion clearly a research program that is very productive. I'm very impressed by some of what I've heard with about the possibilities of retired light and new understandings of that, and then that being part, and to be able to quantitatively test that with near space environment testing, which we potentially now have. So I think we have the beginnings here with this group of putting together a research program that could be very helpful in moving us forward to a new epoch with cosmology. Thank you.
Sahil, you haven't spoken, so go ahead.
Hi, Eric, and thank you for organizing today's event. I wanted to make a few comments. One is, I think the progress that we've made is amazing because almost every YouTube Astro channel is aware of your work, Lerner's work, and despite the excessive criticism, I mean, that means that people are watching, and on top of that, the very popular podcaster Joe Rogan is aware of you. So that is a huge achievement in
Right, I
terms of
saw that.
recognition. Despite, he he says a lot of crazy things. The fact that he's willing to engage and perhaps interview you at some point is very promising. So that to say, the progress has been huge in terms of awareness and distribution. Also, two other comments. I think that in presenting the redshift data, we should avoid using the Z index because that's not a physical quantity. I really prefer the frequency ratio of frequency that we've measured divided by the frequency at time of emission, or the energy ratio, because that's a physical quantity, and that enables just visual interpretation more easily, because it's not some Z index 1/1 plus Z. That's a little confusing. Also, I'd like to suggest that instead of tired light or light fatigue, that the phenomenon be called photon hubbling, because the word hubbling it's a new word. Hubbling is a compliment to Edwin Hubble, as well as it sounds like light losing energy, and it avoids all of the negative stereotypes of tired light. So I'd like to nominate that phrase, photon hubbling, to describe the phenomenon. And that's it for me.
Well, I certainly agree with you that astronomers can use a lot of help with terminology. I think compared with the other physical sciences, the astronomical terminology is a mess, and many astronomers seem proud of it. Okay, Alessandro, you have your hand up. Alessandro
Yes. Hi.
Spallici.
Yes, correct. So I just have this point, and I will introduce it by referring to what you discussed just now, falsifiable and falsifiable. A scientific statement can be wrong because it's been falsified, or a non-scientific statement can be right even if it is not falsifiable. So let me now refer to this strange situation when we talk about the expansion. We know the expansion is supposed to occur locally and not a large scale. Sorry, it will occur at large scale, not locally, which means that beyond our galaxy, there must be a metric, a general relativistic metric, which connects a non-expanding galaxy with an expanding intergalactic space. But anyway, the fact that the universe is not expanding locally renders the Hubble expansion actually, from the technological point of view, unfalsifiable. Because locally, we can't, if we find nothing locally, it means that we have no proof that the Hubble expansion occurs, but that's what the cosmologists of that nature affirm. On the other hand, if we were to try and find a difference in frequency locally in a laboratory, this is extremely difficult. And to my knowledge, I've polled a number of experimentalists so far, and they didn't give me any hope. The 70, whatever the Hubble tension is, 70 kilometers per second per meter, per megaparsec, corresponds to 2.3 10 to the minus 18 meters per second. And this translated in a laboratory scale, and this translated as a static shift, where the universe is not expanding, is around 10 to the minus 26 delta F over F. And 10 to the minus 26 delta F over F is far beyond, to my knowledge, what can be measured in a laboratory. Now, if you have different, different data, I'm very much interested in getting them.
Right now, the best instruments can measure differences in frequency of 10 to the minus 17. I believe they may be up to 10 to the minus 18. And if you do the arithmetic, you look at the planned LISA array. Now, admittedly, this planned array has never been funded, but it certainly is technologically feasible. Planned LISA array would have spacecraft spaced 5 million kilometers apart around the Lagrangian point. And if you do the arithmetic, you can basically, it would take a lot of advocacy to get such instruments on board, especially since LISA itself isn't funded. But instruments that we now have, if they were on board an array like LISA with 5 million kilometer spacing, in the course of a single year, could easily determine to at least 10% whether a Hubble frequency change is happening within our solar system, which presumably everybody agrees is not expanding. So those experiments are definitely technologically possible on the scale of spacecraft. Yeah, they couldn't be done in a lab on Earth, but they are within our grasp in terms of existing spacecraft technology. So that would be an experiment that would be great to do.
Yeah,
and
sure.
probably could be done for under $1 billion.
Yes. I was in the LISA project for a quantity number of years, and but I'm not an experimentalist. So I asked the interferometry people whether it was possible, and the answer is, well, no, forget it. Now, but I agree that is the way to proceed, because in absence of a physical theory that explains tidal light from A to Z, and in absence of an experimental confirmation of a frequency shift not due to expansion, I think we are facing two very big problems.
I have two short comments first for Alessandro Trinchera. You were mentioning the solar limb redshift that is caused by tired light or photon hobbling in electrons. There's also another effect. I think it was proposed or mentioned by Ari Brynjolfsson, maybe, or is that the energy lost by the photons ends up in the electrons in the plasma, and it heats up the plasma, and to a high temperature that corresponds to the solar corona heating. Because you certainly know there's a problem there. Nobody can explain why the solar corona is so hot. That's positive points for tired light. It's just the light that heats it because it gets redshifted. I'm not sure. I think it's Brynjolfsson who mentioned that, but many people have mentioned that too. I don't know if you were aware of this, but
yeah, I was aware of this.
Okay, yeah, it's another point to bring when to help push tire lights, I guess.
Yes. And so far I've just analyzed the center to limb problem, and the redshift problem of the Pioneer 6 space probe, which is directly related.
Yes, also, yeah.
Problem. But it's a good input for the next manuscript to propose.
Yes, of course. Yeah. And the other point was to Alessandro Sparici. It is true. I have worked, I'm an experimentalist, I've worked with interferometers, and the problem in trying to measure the redshift between the satellites like LISA is that they use the lasers to stabilize the distance between these satellites. So if there is a redshift, let's say a tired light redshift, then the distance between the satellite will be compensated to approach very slowly to produce a blue shift to compensate. And so they will think that the system is stable, but that will cancel the effect they want to see. And so the only way to measure the distance is the only way to measure how it varies. And so the experiment is very difficult. I agree with Alessandro.
we're talking about two different things. You can measure distances unambiguously by time of flight.
Also, yeah, but that's less
And,
accurate.
well, it depends on how much time you give it. In
Yeah.
other words, if you're measuring, locations over the course of a year, you can get more and more accuracy. I mean, I'm not an experimental specialist in interferometry.
It's not an easy experiment.
But what?
It's not an easy experiment. It can be done, but it's not easy.
Right.
Yeah.
I assure you, I don't think anything in experimental physics is easy. Theoreticians have it easy. But let's put it this way. It is not far outside the capabilities of existing technology. So I don't think it's an impossible experiment. And you would basically be measuring position of the satellites independently of the frequency of the laser light that they're sending back and forth. I mean, one thing I want to propose concretely for people to think about is, Riccardo and Renato and I will be writing papers based on the surface brightness. I certainly would invite Alessandro, Trinchera, and Rajendra to basically send what results their formulas would predict for this data that we can test, because as Lois was pointing out, we'd have to test each individual model, we'd have to vary the samples and so on to be consistent. But it's relatively easy because we're dealing with relatively small numbers of galaxies. So I don't know whether this would be in the first paper, but it's certainly something of interest. I mean, what are the specific formula for distance, luminosity, and so on for these various models? So this would be a fairly clear-cut test. I would like to ask the audience, quite a few people still left in the audience that haven't spoken, if anybody's interested in commenting or raising a question.
Some topic that was mentioned, indeed related with the seminar, with the talk by Alessandro Trinchera, and also Luis Marmet asked about it, the solar limb, the redshift in the solar limb. Beware that this is an old topic that was already treated in the 70s and the 80s, but beware that the solar physicists have an explanation for this redshift in the solar limb, and there are publications in the 80s and the 90s. So we don't need to change the physics just to explain this redshift. There are conventional explanations in terms of solar physics. I'm not an expert in solar physics, but I know there is literature in that, and the experts in solar physics have no problem to explain the solar limb redshift. So only that.
That's right. They don't have the explanation for the heating of the solar corona, though.
Yeah, true. Yeah.
Well, but plasma physicists do. I mean, this is a phenomenon that is extremely relevant to what we do in the lab, which is the creation of plasmoids, which in our lab are tiny things of a fraction of a millimeter, but on the sun, the plasmoids are about the size of the Earth. And a plasmoid is a way in which magnetic fields kink themselves up, concentrate energy, and then release the energy in the form of powerful beams, which are quite capable of heating plasmas to extremely high temperatures. So I'm not saying that the problem has been completely solved, but there is a lot of plasma theory that can explain the heating of the corona to very high temperatures. So this is not, again, as with a solar limb, this is not something that is totally mysterious and absolutely demands a different physical explanation. I do have one question for Alessandro. The density, I've looked at, plasma and other physical redshift mechanisms, and one of the things that they all run into is that they require a higher density than we observe. I mean, it seems to me, have you considered the fact that a density of, I believe, you were quoting 2 × 10⁻⁷ particles per centimeter cubed, wouldn't that create gravitational effects that are much larger than we observe? And wouldn't that also contradict the observations that Francesco pointed out, that even on the scales of tens of megaparsecs, the density is changing quite rapidly, just because of a greater sampling space. So have you considered, the observational consequences of necessitating such a high density?
I mean, in the case of the solar corona, we have a really high electron density.
No, I'm talking about the cosmological density.
In the intergalactic medium. So in this case, there are some predictions from observational data that states that the number electron density is 0.5 electrons each cubic meter. And so we based our predictions on this value in order to obtain, develop the calculations. And no, I didn't take into account any gravitational possible effect on the variation of the electron density, because, the electron density is just on the order of the 0.5, 0.3 electrons each cubic meter. And if we approach gravitational effects or some effects relating to the space-time curvature, we have to then go in deep into general relativity, as mentioned before. I don't know if I answered properly.
Well, we should offline. I'd like to see what references you have, because it's about more than an order of magnitude more than the observations that I've seen. But we should do that offline.
Okay.
Okay, Rebecca. Somebody new.
Hello, everyone. Thank you so much for your presentations. They have largely been over my head because I'm a layperson, but I do have I have a lot of questions, but the one I really wanted to ask was for Dr. Gupta. I've been following the media coverage around the possibility of the universe being 26 billion years old. And I was wondering, has your interactions with Eric Lerner and the other people that have, rejected the Big Bang proposal, lambda CDM, has that given you are you now considering that possibility of ditching it? And if not, why not?
I don't ditch anything unless it is proven conclusively. We have a lot of ideas, a lot of theories are there, but see, lambda CDM itself is a very strong model. In its own domain, it works very well, as has been expressed by others. But then it has limitations where it doesn't work. Where it has limitations, we can propose a lot of theories. And what I have proposed is one of the theory. It accidentally gave such a huge age of the universe, twice that of the lambda CDM. But really, the thing is, we still have to test that model, whether it fits the other things which lambda CDM already does, and then does it make some new predictions. So I think it's in very early stages, I would say, of this theory, that it got so much media traction. I never thought it would, but accidentally it did.
Rajendra, that's what I don't understand, is why do you say that LCDM right now in 2023 is a strongly supported theory. As far as I can see from the literature, every single data set, the predictions are strongly contradicted by observations, except for the one exception that the correct prediction of the deuterium abundance. Helium is wrong, lithium is wrong, homogeneity is wrong, isotropic is wrong, large-scale structure is wrong, the Hubble constant, which is a prediction from LCDM's model of the CMB, is wrong. You know, there's this long list of anomalies. There are no, other than deuterium, there are no correct predictions. So why do you think that it's a strong theory at all?
You have to ask 99% of other astronomers other than me who say it is a strong theory.
That's a popular theory. It doesn't mean it's a right theory. Science doesn't run on popularity.
You can always suggest many alternative theories, but then they have their own problems. So, and lambda CDM has a lot of problems, but maybe the problems it has are fewer than those of the other theories, that's why other theories are not so well accepted. I don't know, because I don't want to debate on this subject personally, because I would say, as has been suggested by Rebecca, that, you know, we have to really see what I have proposed is not suggesting that expanding universe is right or not. I'm not even saying lambda CDM. I myself have seen in the model I have proposed, lambda CDM plus tired light doesn't really resolve the impossible early galaxy problem. So there has some limitation, but it still is expanding universe is right or not. And you, Eric, you are a believer of, and you have given proofs that expanding model or Big Bang may not be the right thing, and it is this, and you are more in favor of the regular one. So I'm not sure, you know. Sorry.
Okay. Did somebody else
answer your question?
I'm sorry, Rajendra?
I'm just saying, did it answer the question, Rebecca? I'm not sure. Or you have something else to say?
Well, I am still waiting to hear the good evidence for it, because every time I hear on the media, oh, you know, there's so much evidence for it, and then when you narrow it down, it's really, they say the CMB and the redshift, right? There's nothing else, but CMB was off by an order of magnitude. I mean, the prediction was off, and you know, who knows what CMB could be, and then the redshift, you know, that's just an interpretation. So I'm still waiting to hear what the Big Bang is doing for us. Where is it strong for us? Because as I see, and like I said, I'm just a layperson, but I see more and more imaginary entities being made to try to salvage this theory. And so I hear you saying it's strong, but I don't hear you saying why it's strong.
Yeah, I think this is a very good position you have. I would say all we can see is the existing Big Bang model has given us certain directions and certain controversies. What I have proposed is push back the Big Bang time. And maybe the Big Bang, Eric is pushing back Big Bang time to infinity. So essentially, there's the possibility there's something in between which might exist, you know. or it could be a cyclic universe. So I think there are so many possibilities we cannot explore in this small time frame we have here for us. So I think that's where I will conclude my remark.
Thank you so much.
You're welcome.
Unless you wanted to talk about some resources available.
So there's a mailing list. A few of you are on that mailing list. It's the cosmology group. If you're interested, that's where people like you who are interested in cosmology and in understanding what's going on with the Big Bang and other theories. The list has many people who communicate. There's about, I don't know, 20 emails sent every month, so it's not too much, and it's kind of a central resource. There's a website as well, cosmology.info. You can visit, and there are all sorts of papers and presentations and all that. So it's an old group, and it's been, I think there's been many interesting discussions on that mailing list, just like the ones we've had today, and it's a chance to talk to other people who are also kind of agree that, you know, it's worth examining the Big Bang and theory and questioning it. So if you want, you can send me an email. I put my address in the comments there, the chat. And I can register your email, and we can have discussions over there too. So.
I just want to say we are going to put this video on our YouTube channel, which has about 12,000 subscribers. We will put the presentations up on our own LPPFusion website, and I think that we should, with everybody's permission, also put them on the info.cosmology website that Louis was referring to. We want to get this discussion more circulated. I do think that it will be more, there will be more open discussion going forward, just judging by this recent conference, online conference of the STSC, in which the observers were certainly expressing a good deal of, I won't say concern, I don't think they were concerned, but a good deal of emphasis on the conflicts between observations and the predictions of existing theory. So I think this discussion is going to broaden out. I really thank the participants for presenting here, including the ones who didn't last to the end. Martin, you stayed up really late there in Beijing.
Thank you for the organization. Yes, I was interested.
We definitely will make this the first of, we hope, a series of broadening discussions and workshops on the question of the expansion of the universe and whether cosmology is indeed a real science, which I think it is. So thanks to all, and let's stay in touch.
Thank you, Eric.
Thank you.
Okay.
Thanks to you, Eric. Bye.
Take care.
Hey,
Bye-bye.
bye.
Thank you.
Bye-bye.